Now I'm going to talk about how the neuromuscular system will adapt. There are many different adaptations that the neuromuscular system will make. One of the adaptations is that the muscle fibers types will adapt. There will be hyperplasia, which is an increase in the muscle fibers. For example, a long-distance runner will train for muscular endurance and cardiovascular fitness. Because they are training in this way, their slow oxidative muscle fibers will become thicker and therefore they'll be able to run further for longer. On the other hand, if you're a sprinter, their fast glycolytic fibers would be thicker and therefore there will be more fatigue. However, my hockey player will use mostly fast oxidative glycolytic, as she'll be working anaerobically and aerobically. Moreover, she will have bigger myoglobin stores. This is an advantage as she will have more oxygen available in her muscles ready to use. This means that she could work harder for longer and her slow oxidative muscle fibers will be able to work for longer. Moreover, there will be bigger stores of mitochondria. This is the site of aerobic respiration and ATP is produced from it. This links into the energy systems as ATP is the starter of all the energy systems. Moreover, another adaptation is tendon and ligament strength. The stronger these are, the less chance of injury on the pitch. So, for example, the hockey player, there'll be less chance of you rolling your ankle as the ligament will be stronger. Moreover, the fast oxidative glycolytic fibers, known as the fog fibers, will get stronger and they'll get thicker. The hockey player will experience this as she is working both aerobically and anaerobically. Also, the neuromuscular system pathways will adapt. The neuromuscular pathways will adapt, and the impulses will be able to send quicker, which means that they'll have a quicker firing of the SA node, which will result in quicker reaction time. So for the hockey player, she needs to have quicker reaction time to be able to stop the ball or intercept someone to get the ball. This will also result in proprioceptors being able to detect changes quicker. Here is some data from the Wingate tests. As you can see, Sir Chris Hoy gets peak power of 2,200 watts. This is important in the sport as he needs to have a lot of power in his legs to go fast, as he can on the bike. As you can see from the data, the typical male student peak power output is 750 watts, which is less than half of Sir Chris Hoy. However, if the student trained, they'll be able to get a higher peak power as they would have more power in their legs. This data shows the peak power output and fatigue index of individuals in a class. Fatigue index, as you can see, Charlie White has the highest fatigue, whereas Ellis has the lowest. However, when you look at Ellis's power output, you can see that it's only 609 watts, whereas George is almost double Ellis's. George's fatigue index was only 6% higher than Ellis's. This could be because George plays rugby and therefore he needs more power in his legs in order to drive the balls forward. On the other hand, Ellis plays football. Even though he needs a lot of power in his legs, he only needs it to be able to kick the ball. If he did training on his lower body, he would adapt to training and his muscles would grow into hypertrophy and will result in the muscles being more powerful, and overall this results in bigger peak power output. This graph shows the Wingate anaerobic test and it shows the tolerance to lactic acid buildup. The star shows where the peak power is and the line shows the fatigue index. This is how much the individual has fatigued from their peak power to the end. The red line will roughly show a 100-meter sprinter, as they would have a higher peak power output as they have trained to reach their maximum quickly in around 10 seconds. Therefore, they are likely to have a higher fatigue index. The green line shows a longer distance runner, for example 1,500 meters. This shows them as they don't build up as much peak power and it takes them longer to get to their peak power. Moreover, a long distance runner will have a lower fatigue index than a 100-meter sprinter. This is because a sprinter will build up more lactic acid as they have a higher peak power output. Now I'm going to talk about the energy systems. There will be an increase in anaerobic and aerobic enzymes. This is important because you need the enzymes to make sure that reactions can happen. Without the enzymes, For example, ATP couldn't break down into ADP and glucose couldn't go into glycogen. Moreover, there is an increased use of fats as an energy source, so this is also known as glycogen sparing. This is important as it saves the glycogen and uses fats instead. Moreover, there is a delay in lactic threshold and OBLA, and the tolerance to lactic acid, but I will talk about this in the next few slides as I compare this with the data. There will be an increase in VO2 max, so aerobic respiration and increased anaerobic respiration. Moreover, there will be more mitochondria in the muscles ready for use straight away, as mitochondria produces ATP during aerobic respiration. This graph shows the rating of perceived exertion. This graph is showing the RPE of an untrained athlete. However, an untrained athlete would most likely show the RPE, and to say a trained athlete would likely be shown RPE and be able to stay lower for longer. This is because they shouldn't find exercise too hard if they've been training in the black line shows a trained athlete as they shouldn't find this test too hard. Moreover, they will be able to carry on the test for longer. This graph shows a blood lactate profile. The blue lines show the lactate of an untrained athlete. OBLA is usually measured at 4 millimoles. The black line shows a trained athlete. It will be lower because they have learned to tolerate lactic acid. Moreover, the more they train, the better their tolerance would be. Lactic threshold occurs at a higher percentage of VO2 max, from a greater ability to clear lactic acid from muscles and from an increase in skeletal muscle enzymes. Now I'm going to talk about the skeletal adaptations. So, weight bearing or resistance would help in bone density, so you'll get stronger bones because more calcium will build up. So this will lead to bone density increasing. Overall, this will reduce the risk of osteoporosis. Also, you'll get stronger tendons and ligaments. Stronger tendons because the thickness of the tendons will increase, and the ligaments are there to help stabilize the joints. Also, functional mobility and independence. So as you get older, you're able to be stronger and therefore you're able to do day-to-day activities like walk up the stairs. Also, you'll have a better range of movement at the joint. Moreover, cartilage gets thicker, so if the cartilage is lost, then you get pain, so this is when bone rubs on bone. Moreover, skeletal adaptations will help reduce the chance of injury. It's important to have increased flexibility, the thickening of cartilage, and an increase of strength of the tendons. This is because, as a hockey player, you need to be able to reach out for the ball, so that's flexibility. You need to be able to bend down to hit the ball. Also, the thickening of the cartilage will help the reduce of pain and reduce of friction. And the increase of tendons will help reduce injury. So overall, all these systems will adapt due to what exercise you're doing and what training you've done in the past.